Hi guys, so today we are looking at theoretical probability of simple events. Alright, so at a school fair, we have a choice of spinning either spinner A or spinner B, and we're going to win an MP3 player if the spinner lands on a section with a star in it. Which spinner should you choose if you want a better chance of winning? Okay, let's go ahead and take a look at spinner A first. First, we want to find total number of outcomes. So when we look at spinner A, we can see that there are 1, 2, 3, 4, 5, 6, 7, 8 total outcomes. And then number of sections with stars. Spinner A has 3 sections with stars. So the probability of winning on spinner A would be the number of sections with stars over the total number of outcomes. So that would be 3/8, and I can turn that into a decimal, which would be 375 thousandths, or as a percent, 37.5%. Let's go ahead and take a look at spinner B. Wow, a lot more sections here. Okay, let's count carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total outcomes. And we have 1, 2, 3, 4, 5 sections with stars. So the probability of winning would be 5 out of 16. And when I turn that into a decimal, I get 3,125 10,000ths, which is equal to 31.25%. All right, so the ratio for spinner blank is greater than the ratio for spinner blank. Which one had a higher ratio? Well, I know that 3/8 is greater than 5/16, and I know this two ways. First, the percentage is definitely higher. But second, if I were to rewrite the fraction for spinner A using 16ths, so I had a common denominator to compare them, I can see that 6/15 is more than 5/15. So spinner A is greater than spinner B. So if I want to win, I have a higher chance using spinner A. All right. So theoretical probability of simple events. Remember, to calculate probability, we take the part we're interested in, the part that we're curious about, and we put that as our numerator, and then the total number of things that can happen is going to be our denominator. Once we get our fraction, we can turn it into a decimal and then use that to get our percentage. A bag contains 6 red marbles and 12 blue ones. We select one marble at random from the bag. What's the probability that you get a red marble? Okay, the first thing I want to know is how many marbles are in the bag all together. I know that there are 6 red and 12 blue. So all together, there are 18 marbles in the bag. That's going to be my denominator. Now, the part I'm curious about, remember, we were interested in red marbles. There are 6 red marbles in the bag. That's going to be my numerator. So 6 out of 18, remember that's going to simplify to 1/3. As a decimal, it's a repeating decimal. It looks like this. So when I multiply it by 100, my percent is going to be 33.3 repeating percent. So the probability of getting a red marble is 1/3, or 3/10 repeating, or 33 3/10%. All right. We roll a number cube one time. What is the probability that you roll a 3 or a 4? Write your answer in simplest form. Well, the first thing I want to know is when I roll a number cube, how many things can happen? Remember, when you roll a number cube, you can get a 1, a 2, a 3, a 4, a 5, or a 6. That's a total of 6 things. That's always going to be our denominator. Now we're curious about getting a 3 or a 4. When I look at my list, There's 1 3 and 1 4. So there's 2 things that I'm curious about. That's going to be my numerator. So my probability would be 2 6, or in simplest form, 1/3. So how is the sample space for an event related to the formula for theoretical probability? The sample space is everything that can happen. That's going to be our denominator, our total. Okay, 6 students are performing in a talent contest. You roll a number cube to determine the order of performances. You roll the number cube once. Complete the table of theoretical probabilities for the different outcomes. Now remember, when we roll a number cube, there's a total of 6 things that can happen. You can get a 1, a 2, a 3, a 4, a 5, or a 6. That total is always going to be our denominator. So the probability of getting a 1 has a denominator of 6. The probability of getting a 2 has a denominator of 6. In fact, when we roll a number cube, all of the probabilities start with a denominator of 6. Now for each one, I go back and I check. There's only one way I can get a 1. There's only one way I can get a 2. And in this case, they're all equal. They all have a probability of 1/6. The next part wants us to predict the number of times each number will be rolled out of 30 total rolls. For this, I can use proportion. I know the probability of rolling a 1 is 1 out of 6. That means out of every 6 times I roll that dice, I should get a 1 one time. We want to know the probability of getting a 1 out of 30 rolls. Since 30 is a total, it's going to be a denominator. Now using my proportion, I know that 6 times 5 is 30. So to get my numerator, I'm going to do 1 times 5, which is 5. So out of 30 rolls, we predict we'll get that 1 5 times. Notice everything had the same probability, which means out of 30 rolls, we expect to get each number 5 times. All right, let's try another one. Roll a number cube 30 times, complete the table for the frequency of each number, and then find its experimental probability. Okay, before I turned the camera on, I cheated a little bit and I rolled the number cube 30 times. I got a 1 3 times. I got a 2 12 times, believe it or not. I got the 3 5 times. I got the 4 4 times. I got the 5 3 times. And I got the 6 3 times. Now let's make sure those numbers add up to 30. 3 plus 12 is 15, plus 5 is 20, plus 4 is 24, plus 3 is 26, 24 plus 3 is 27, plus 3 more is 30. So I rolled it 3 times. Now notice, I landed on that 2 way more times than I was expecting to. I landed on the 3 the exact number of times that I was expecting to. So based on this experiment, because it was out of 30 times, all of my fractions start with a denominator of 30. And then my numerators are going to be how many times that number showed up. So for a 1, I got 3 out of 30. That's going to simplify to 1/10. As a decimal, 1/10. As a percent, 10%. For the 2, I got that 12 out of 30 times. That's going to simplify, let's see, 6 out of 15, and 3 is going to divide both of those 2/5. So as a decimal, that'll be 0.4 or 40%. 5 out of 30 is going to simplify to 1/6. 1/6 as a decimal, we get 0.16 repeating. So as a percent, that's going to be 16.6 repeating percent. 4 out of 30 will simplify to 2 out of 15. As a decimal, that's going to be 0.1333 repeating. So as a percent, that'll be 13.3 repeating percent. We know that 3/10 is one, or 3/30 is 1/10 as a decimal, 1/10 and 10%. And this one is the same as the 1 and the 5. So we'll just write that in really quick. So look at the two tables you completed. Remember this one we did where, because it was theoretical, everything was the same. It was all 1/6. This one is experimental. I actually rolled the dice. Are my probabilities the same? For the most part, no. My probabilities are not the same. It was only the 3 that came out the same. A lot of them are very, very different. So my experimental probability in this case was not the same as the theoretical probability, except for that 1 3. That one showed up exactly how many times it was supposed to. All right, can the experimental probability ever be exactly equal to the theoretical probability? Now, if we look at the experiment we just did, the experimental probability for rolling a 3 was the same as the theoretical probability for rolling a 3. So it can happen. How likely is it to happen? Not very likely. And the reason why is because we're actually doing a real world experiment. We can't control it and make it perfect every time. But if you remember back to our statistics unit, sample size. In my experiment, my sample was only 30 rolls. If I increased that sample size, I'm more likely to get results that are going to match the theoretical probability. Okay, guys, I'm going to go ahead and make the video for day 2, so I will be right back.